Hello everyone, you are on the channel Who Created It and How. Today we're looking up, way up, at one of the most majestic and awe-inspiring architectural features ever conceived. The dome. From ancient temples to modern stadiums, these soaring structures have captivated humanity for centuries. But have you ever wondered how they were actually built? How did ancient engineers, without modern cranes or computer models, manage to create these massive, self-supporting ceilings? It's a story of genius, innovation, and a whole lot of physics. So let's dive in and uncover the secrets behind how they constructed domes. The story of the dome begins thousands of years ago with the simplest form, the corbel dome. Imagine stacking rings of stones with each new ring slightly smaller and cantilevered inward over the one below it. You keep going, layer by layer, until the rings meet at a single point at the very top, called the apex. This was one of the earliest methods used in structures like the Treasury of Atreus in Mycenaean Greece, built around 1250 BC. It's an incredible feat of engineering, but it has its limits. Corbel domes create immense outward pressure, meaning they need very thick, heavy walls to keep them from collapsing. This is why you often see them built into hillsides, or with massive earthen mounds piled against them for support. It's a brute force approach, but it was the essential first step. The most magnificent example, of course, is the Pantheon in Rome. Completed around 126 AD, its dome is still the world's largest unreinforced concrete dome, nearly 2,000 years later. Its construction is a masterclass in structural engineering. To manage the immense weight, the Roman builders got incredibly clever. They started with a thick 21-foot base and gradually thinned the concrete shell as it rose, making it only about 4 feet thick at the top. They also used different aggregates in the concrete mix. At the bottom, they used heavy travertine and tufa, but as they went higher, they switched to lighter materials like crushed volcanic rock and pumice. And the most iconic feature, the oculus, that giant opening at the top, isn't just for light. It actually removes the weight from the dome's weakest point, the apex, and turns the downward force into a compression ring, further strengthening the structure. It's pure genius. To build these massive structures, the Romans used extensive wooden scaffolding and centering. Imagine a huge, complex wooden framework built in the exact shape of the dome's interior. This framework would support the concrete molds and the concrete itself as it cured. Once the concrete was fully hardened and self-supporting, this massive wooden structure would be carefully disassembled and removed from the inside, revealing the breathtaking space above. It was a hugely labor-intensive and resource-heavy process, but the results speak for themselves. The Pantheon has survived earthquakes, fires, and centuries of neglect, a timeless testament to Roman ingenuity. After the fall of the Roman Empire, dome building techniques evolved, particularly in the Byzantine Empire. Their architects faced a new challenge: how to place a circular dome on top of a square building, which was the preferred layout for their grand churches. Their brilliant solution was the pendentive. A pendentive is a curved triangular section of a vault that bridges the gap between the corner of the square room and the circular base of the dome. It looks like a slice of a sphere, smoothly transferring the weight of the dome down onto 4 massive piers at the corners of the square. This innovation allowed for even larger and more open interior spaces, creating a sense of heavenly light and volume. The ultimate expression of this technique is the Hagia Sophia in Istanbul. When it was completed in 537 AD, its central dome seemed to float magically above the congregation, supported by 4 massive pendentives and flanked by semi-domes. The architects, Anthemius of Tralles and Isidore of Miletus, were mathematicians, not builders, and they pushed the limits of what was thought possible. The dome appears almost weightless, an illusion created by a ring of 40 windows at its base. These windows not only flood the interior with light, but also visually separate the dome from its supports, making it seem as if it's suspended from heaven by a golden chain, as one contemporary described it. The Hagia Sophia defined a new era of dome construction, influencing church and mosque architecture for over 1,000 years. As we move into the Renaissance, we encounter one of the greatest architectural challenges of all time, the dome of the Florence Cathedral, or the Duomo. By the early 15th century, the cathedral was mostly complete, but it had a giant 140-foot wide octagonal hole in its roof. No one knew how to cover it. The space was too wide for traditional centering, and the city of Florence didn't have enough timber to build it anyway. The competition to solve this problem was won by a goldsmith and clockmaker named Filippo Brunelleschi. He proposed a radical solution: build the dome without any central scaffolding at all. Brunelleschi's design was actually 2 domes, one inside the other. The inner, thicker dome provided the structural support, while the outer, thinner dome protected it from the elements and created a more imposing profile. The 2 shells were connected by a system of massive stone and wood ribs. He used a special herringbone brick pattern, which allowed the bricks to grip each other as they were laid, preventing them from falling inward before the mortar set. He also incorporated horizontal tension chains made of stone and iron, like hoops around a barrel, to counteract the outward pressure. To get the materials up to the soaring heights, Brunelleschi invented a revolutionary ox-powered hoist with a reversing gear, a piece of machinery far ahead of its time. It was an incredible feat of project management and engineering, and his double shell design became the new standard for monumental domes for centuries to come, influencing everything from St. Peter's Basilica in Rome to the US Capitol in Washington, D.C. The story doesn't end there. In the modern era, new materials and technologies have completely transformed how we build domes. The invention of steel and reinforced concrete in the 19th and 20th centuries allowed for structures that were lighter, stronger, and more versatile than ever before. This led to the creation of the geodesic dome, popularized by Buckminster Fuller in the mid-20th century. A geodesic dome is a spherical or partially spherical shell structure based on a network of triangles. These triangles distribute the stress across the entire structure, making it incredibly strong and efficient for its weight. They can be built from lightweight materials like aluminum or steel struts, and can cover enormous spaces with no internal supports. Think of the iconic spaceship Earth at Epcot Center in Florida. That's a perfect example of a large-scale geodesic dome. Today, we have even more advanced techniques. We use inflatable membranes as formwork for concrete domes, tensile structures made of fabric pulled taut by steel cables, and computer-aided design to model and test complex shapes before a single piece is ever built. Domes are used for sports stadiums, exhibition halls, and scientific research stations in extreme environments like the South Pole. From stacking stones in ancient Greece to designing complex grids on a computer, the quest to build the perfect dome has consistently driven architectural innovation forward. It's a journey that spans millennia, connecting us to the genius of our ancestors and pointing the way to the incredible structures of the future. What a legacy! Thanks for joining us on Who Created It and How. If you enjoyed this look into architectural history, don't forget to like, subscribe, and hit that notification bell so you don't miss our next adventure. See you next time.